Good morning. Today we are doing Paul Hewitt's Conceptual Physics, Chapter 22 on heat transfer. Okay, so heat transfer. We've talked a little bit about that last lecture. What is heat? Heat is, remember, kinetic energy, but on a molecular level, those little molecules vibrating and whatnot. There are three ways that things transfer heat. Conduction, convection, and radiation. So conduction, you've got the literal contact and you've got the molecules from the hotter thing vibrating and shaking the molecules from the cooler thing. So remember the cold hand holding onto the warm hand. The molecules in the warm hand are vibrating and sharing some of that thermal energy, that molecular kinetic energy with the molecules in the cooler hand. Or with the example, the guy with the frostbitten foot sticking out his friend's shirt, his cold foot, the warm vibrating molecules in the one man's warm chest are helping vibrate the cold molecules in the cold guy's foot. So metals are really, really good at transferring heat. As you know from you don't open the oven and touch a metal pan in the oven. You know that's really, really hot. Because metal is extremely good at conducting heat, at moving that heat from the hotter temperature to the cooler temperature. Remember, that's what heat is. Heat is the transfer of what we call thermal energy, internal energy, kinetic molecular energy, moving from the hot temperature to the cool temperature. That is what heat is. And so metal is extremely good at conducting that heat. That's why you don't open the oven and grab the metal pizza pan with your hand and pull it out. Instead, you open the oven and you put on a rubber glove, not a rubber glove, a thin little rubber glove, but like those really thick silicone gloves, or you would put a thick cotton glove on your hand before you transfer it. Why? Because the cotton oven mitt has a lot of air pockets in it. And remember, air is a poor conductor of heat, or we like to say a good insulator. Remember, a good insulator means a bad conductor of heat in this case. And remember, a good conductor means a bad insulator. So remember, metal is a bad insulator. It's a wonderful conductor. Like a cotton fabric with all those air pockets. Remember, it's air. Air is a bad conductor and a wonderful insulator. So remember, a lot of our insulative materials, we try to hold pockets of air in it. Or even better, vacuum. But anyways. So, right, we did that. Okay, so insulation delays heat transfer. It can't completely stop it from ever happening. Like if you sit there and you have your hand in the like touching the oven rack, holding your cotton glove, and you wait and you wait and you wait, yeah, eventually the heat's going to get to you. But what a good insulator does is it delays that heat transfer from happening. That heat transfer is still happening. A good insulator just makes it take a really long time. All right, so that was conduction. So that's the easiest. You have both surfaces touching, and you have the heat traveling. Okay? So what about convection? Now we're going to talk about convection. What is convection? Well, convection is heat transfer by currents in a fluid. So a lot of times people talk about convection ovens. Convection ovens usually have some form of forced air moving it around. So here, the difference between conduction and convection is in conduction, you have the two materials that are having the heat transfer actually touching each other, contacting each other. In convection, you have it running back and forth. Okay? So you have a liquid that is running back and forth, moving that heat. So convection, people will often draw these little pictures like this. Conduction, you could say you've got the two surfaces actually making contact, okay, and the heat transfer. Convection, say we've got one object here, one object here. We've got a fluid, whether that's a liquid or a gas, that is doing convection to move. So say if I've got a thing of water here, and I've got a red hot piece of steel and a cool piece of steel, and the water is taking some of that heat molecules and going and not heat molecules, excuse me, he's taking some of the heat from the molecules, some of that heat energy, and is moving with the water now shaking and then warming up the other thing. So convection, you've got like a fluid, a medium, that is moving the heat energy from the hotter object to the cooler object. Big example of this is basically ocean currents. We talked a little bit about how the warm water from the Caribbean gets up through the Gulf Stream and warms up Britain and places like that and keeps it from being frigid like northern Canada, which it would be if it wasn't for the Gulf Stream. So convection, we see that a lot with our ocean currents. We see that a lot of wind currents, with winds that have patterns circling around the world and how they move hot air and wet air and dry air and all that. So if you do any sort of meteorology, convection is very, very important to you. And another example is sea breezes, that because you remember the high specific heat of water, as the sea during the daytime, the sea is actually cooler, because you remember the high specific, so the sun is warming up both the land and the sea, and remember the sea, it takes a really long time to warm up. So the sea during the daytime, the sea is cooler than the land. The land heats up much faster, like the iron heats up much faster than the water. And so the land will heat up much faster, and so the land will be hotter, and this means that the air over the land will get hotter, and it will rise, because remember hot air rises. And this will kind of suck the cooler air. That's why you get those lovely sea breezes. Will suck the cooler air, because if this air is going up, there's like a vacuum, it sucks the cooler air in from the sea. This is convection. Well, then what happens to the hot air? It gets up, it cools off, then it comes back down, makes better contact, and you get these sea breezes going during the day. During the night, it's the opposite way around. During the night, the earth cools off pretty quick, and the water with a high specific heat is still holding on. So the air over the sea is warmer, so it will rise, and then will suck the air off the land, and then you get, convection, you get this, it rises, it cools off, it comes down, it gets warm again, and it goes off, and you get these, that's why people that live near the sea, they talk about the sea breeze, and it goes a different direction during the day and during the night. That is convection. But you need a medium for convection. You can't have convective heating in a vacuum. Is it recording?
Yeah.
You cannot have convective heating in a vacuum, because in a vacuum there is no medium to move. There are no particles that are moving. They're being that conduit for the heat.
So is that why is it going to be really cold in a vacuum?
Well, that's why people talk about, what? Really cold in a vacuum? Well, it depends. If you're sitting, because there's other ways of getting heat in a vacuum. So this is, that's why convection, if you think about it, like if you're in shade on a hot day, you're still warm. Why? Because like all the warm air and everything else,
the bird flew into the window.
Okay, I'll check
it flew away.
Okay, good. All right, so another, but if you're in space and you're just like in shadow in space in a vacuum, like there is no warm air that's traveling from the warmer spot and coming to warm you up. You're just cold. That's why places with no atmosphere, because the atmosphere, it's like specific heat holding it on and whatnot. If there's no atmosphere, then if the sun's shining on you, you're really, really hot. If the sun's not shining on you, you're really cold. Anyways. Okay, so back to, that was convection. So remember, convection needs a medium to bring the heat from the hot object to the colder object. Okay? Conduction, they're touching. Convection, there's a medium. And radiation. Radiation is very cool. And radiation is the light, well, everything, all light we see is radiation, heat we see is radiation, has to do with the electromagnetic spectrum that we will talk about in a few weeks, which is really, really, really cool. And this is radiation. Radiation does not need a medium to travel, which is a really good thing, or we wouldn't get any of the warmth from the sun if it needed a medium, because the sun's light and heat travels through all those just vast, vast reaches of space, through a vacuum, and gets to us, and it can warm us up just fine. It's not relying on convection. We're not touching the sun. It's not conduction, but we get that radiation to us far, 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 far away, to our little planet. Now, so as I said, radiation travels in a vacuum. That makes it different, because it's going from point A to point B across a vacuum. They're touching. Here, convection, remember the medium that's traveling it, moving it, and radiation, here we have it going straight over. Now, radiant energy, like our sun, when it hits something, it heats up that object, and that object will also radiate stuff back out again. That's how we see anything. When I look, I'm seeing the light from the windows or the lamp there is bouncing off of that bookshelf over there and bouncing to my eye, and I can see the light. Now, as you probably know from middle school science, the darker something is, the less light is bouncing back, the more it's just eating and absorbing that light. The brighter, like white stuff, is bouncing almost everything back at our eyes, and that's how we see it so well. So remember, good, kind of following the whole, principle of like, with, remember something with a really high specific heat takes a lot of heat to heat it up, but it also takes a lot of heat bleeding off to cool it down. In the same way, a good absorber, like a black object, will get much hotter. If you go outside in the sun, you know that radiative energy from the sun will heat you up in a black t-shirt much faster than a white t-shirt. Now, this doesn't matter for convection. If you're sitting in the shade, it doesn't matter if your shirt is black or white. You're still getting the hot air with a convection. But with radiation, you know that when you wear a black shirt, it's soaking in that heat much faster. An interesting thing is that good absorbers are also good emitters. So theoretically, if you're wearing a black shirt, not in direct sun, you will be radiating just a little bit more of that energy than if you were wearing a white shirt. But I don't think it's a huge difference. I should double check that. Okay, so these are our three methods: conduction, convection, and radiation. But in the book, he talks about if you have a pitcher of warm water, a black pitcher, a white pitcher, and they're not sitting in the sunlight, they're not getting new energy in, so they're just radiating their warm water out. Radiating their heat energy out. The warm water in the black pitcher will actually cool off faster than the warm water in the white pitcher. Okay.
Mom?
Yes.
So, does light go further than heat?
No.
Then
All of them are waves.
So then, do we get any heat from stars?
Tiny bit. Oh, I see what you're saying. Does light go farther? No, but I just think with heat, I think it's more a matter of like how we feel. Like you're getting, okay, the infrared. So if we look at the spectrum, so we're going to cover more later, just touching lightly. We've got wavelength, and as you've probably known from middle school science, red waves look like that. Blue waves look more like this. And if they're bluer than our eyes can see, are ultraviolet. Those are the UV rays that hurt your skin, hurt our skin.
Heat is the big ones, right?
Heat is more red than red. So heat is more like
those
that.
Ones.
That's more red than red. So I think it's also, if you look, this has more energy packed into it than this. So it's not that the distant stars aren't giving us heat. It's just that the amount of heat that you get, because remember, everything's being spread out. Also, our eyes are much, much better at adapting to seeing extremely low light levels, where I think your body, needs to feel more of those heat waves in order to really feel it.
Okay.
I think. Anyway, okay, sorry. So I guess technically we are getting heat from the stars, but it's extremely small amount. Okay.
Wait, is there such a thing as purple light?
Purple light, yeah, sorry. When I say more blue than blue, I skipped purple. More purple than purple, that's what it's called, ultraviolet. And more red than red, that's heat. Okay, so another thing when we're talking about heat being the transfer, remember heat is the transfer from a hot object, a transfer of thermal energy from a hot object to a cooler object. This transfer will happen faster the bigger this difference is. I think that's Newton's law of cooling. Basically, this is the difference in temperature. So whenever you see a delta, that means like the temperature of 1 minus the temperature of 2. So the bigger the difference in temperature, the faster the rate of cooling. Now you know this. This is why when you were a kid and you got something hot out of the oven, it was really hot, and your mom said it has to cool off, you can't eat it yet, whether it was a piece of bread or a cookie, you stick it in the freezer to make it cold faster so you could eat it. We kind of, inherently know that the bigger the differential, the faster the rate of cooling will happen. It's why your heating bills go up like crazy in cold snaps, is that as you're trying to keep your house warm and it's cold outside, and if it gets really cold outside, your house, even with the same level of insulation, if it's like 20 below versus if it's like 20, above zero, your house will be radiating a lot more heat, even with the same, because it's trying to reach thermal equilibrium. The bigger the difference, the bigger the temperature difference inside and outside, the more that heat is radiating out. Or a house, Arizona in the summer, it's 118 outside, the more the heat is, or you could say the more the heat's trying to get in, but it's, about, I guess the outdoors trying to cool themselves by giving us their heat, or you could sort of flip it on its head and think of it that way. Okay, And also why you put this cake in the refrigerator to cool that too. Okay, so now we're going to talk a little bit about the very end of the chapter. We're going to hold on in that chapter. We're talking about greenhouse effect and greenhouse gases, and then tying that in, he talks a bit about global warming. So backtrack, let's talk a little about greenhouses. So the way greenhouses work is you've got, say you're in Siberia and you're trying to say you want to grow plants and it's snowy and cold and it's just too cold for plants. So you build yourself a little glass house and you put your little plants in here. What happens is that the radiative sun energy comes in, and remember, the radiation will just go right through the glass, and you get all that sun energy in here. But instead of having the cold Siberian winds whipping over you and sucking, trying to reach a thermal equilibrium with the cold air outside and sucking, all that warm energy, what happens is that it sort of traps, the energy radiates in, and sometimes they'll even paint the floor of their greenhouse black, try to absorb as much of that energy as they can. I've seen, anyway, so you're trying to keep it warm, and then you're trying to, with the glass there, you're trying to reduce the convective cooling of the, convection of the winds trying to steal that energy back. I mean, yes, you radiate some back out. In fact, there's some Chinese greenhouses where they build them more like this. I've seen like this, and they'll actually have these huge blankets. And then at night, when it's really cold, to stop there from radiating heat out, they'll put a giant blanket over their greenhouse at night, which is very smart. And then they'll roll it off in the morning and let it soak up, more of that sun radiative energy, and then try to keep it from radiating that heat out when they cover it up at night. So a greenhouse gets hotter than the things, outside. Now, if you're not in Siberia, if you're, say, somewhere like Arizona, and you're just trying to keep it a little warmer in your greenhouse because you've got some tropical plants, and it gets over 40 degrees that day, you could kill your plants. Because the sun gets in, and the greenhouse is built to try to minimize the heat radiating out. And it can get super hot in there, over 100 degrees, bam, goes way up. It can get up really much hotter than 100 degrees inside of a greenhouse. And you can literally fry your plants. Oh, sorry, when I'm talking about degrees, I'm talking Fahrenheit. So I was reading a book about greenhouses, and they were like, if it gets over 40 degrees during the day, vent your greenhouse. And they even make little greenhouses where it gets too hot during the day, and so it'll have a little vent.
Do they mean Celsius?
Yeah, so it'll have a little heat vent. And
is it Celsius?
Yeah, no, this is Fahrenheit. Sorry, I'm talking about American units and whatnot. So it'll have a little vent that'll open up and try to let that convective cooling if it's getting too hot. So they have these fancy little greenhouses with these little automatic vents that have to realize, oh no, we're about to cook the plants, I gotta open it up, and then they do these little things. But a really simple way, a really cheap way of having a greenhouse without cooking your plants and it gets too warm, I mean, other than constantly checking the temperature and running in and opening up doors and whatnot, which some really dedicated gardeners do, but an extremely simple way is to put water in your greenhouse. There's, especially people take 55-gallon drums, fill them up with water and paint them black. So you say, what does this do? Remember the high specific heat of water? Well, what's it doing? The radiation is coming in, heats up those 55-gallon drums because they're black. Remember, they're soaking up the energy, the heat energy, and then it doesn't cook during the day because that greenhouse has a big heat reservoir. Instead of the temperature in there cranking up to 200 degrees, all that heat coming in is working on warming up that water. And then what happens at night? It's a little bit like the Chinese blanket. At night, over their greenhouse, at night, now those 55-gallon drums of water are releasing all their heat. So it's a really cheap and great way.
To sleep with the water bottle?
It's a really cheap and great way of making your greenhouse more like California and less like Arizona. You're pulling those high temperatures down, and you're bringing those cold night temperatures up by having painted black 55-gallon drums. There's even people that are trying to grow citrus in kind of colder areas where it's a little too cold, and they'll actually take they'll paint a 55-gallon drum black, fill it up with water, and they'll just stick it right next to the little tree throughout the winter. And it's just enough that it never gets frozen. I mean, it depends on your other temperatures, but it was pretty cool, a pretty cool trick. Anyways, so the world, as you can imagine, is like this greenhouse with a massive amount of water. Anyways, so the water really helps the temperatures on Earth not end up super hot and super cold like Mars that doesn't have all that glorious water.
Wait, Mars is hot?
Mars can get very hot during the daytime in the sun.
But I didn't know that.
I thought.
Are you sure that's not Mercury?
Okay, I may have gotten that wrong. My spacefaring, or my dreams of spacefaring daughter has just corrected me.
Wait,
that may be Mercury.
You're having a video!
Okay, wait, let me finish. Okay, so he talks a little bit about, so that's the greenhouse effect. So the concern that people had was they said, what happened what happens to our Earth? So our Earth, remember, we've got like those 55-gallon drums. We've got so much water on Earth. That really helps regulate the temperatures. But we have this, remember, our atmosphere, so what they call it like the greenhouse glass. We have our atmosphere. Guys, please don't chat, okay? We've got our atmosphere, especially like the ozone layer, the CO2 layer, blah, blah, blah. So these layers, and then what they do is when the sun sends its radiative energy, they kind of trap it and can keep us nice and warm like that greenhouse. And it's a really good thing that Earth has greenhouse gas effects, because if not, so the surface of the Earth would be something like negative 18 Celsius, I believe, which would be, I think that would be like negative, like somewhere around, not exactly, but somewhere around like 32 below 0 Fahrenheit. That's not at all good, but I'm doing astrophysics math here. Anyway, you get the idea. You can go plug in. That's how cold the Earth would be if we didn't have this nice blanket of atmosphere helping block some of that, like the glass on the greenhouse, helping block some of that re-radiating, losing that warmth that we've got. But then there has been people said in the last 5. Okay, so this is if you hold to the theory of the older Earth. And that the fossils are that the Earth is, millions and millions of years old, and that, the layers, the whole 2 different theories of whether did God create Adam as a full-grown man versus like baby sort of idea, except the Earth, not Adam. Like, did God create the Earth with like, all the layers of fossils and stuff already there, like an old Earth, or did he start from scratch and have the mountains and everything grow up in all those years and years? So that whole debate about long Earth, young Earth, there's a lot to be said on those topics. A lot of extremely intelligent people that I've heard argue both sides. Argue the different sides. But this book, it's a secular book, and they're going off of the old Earth. I personally happen to believe more of the old Earth theory. My best friend is the young Earth theory, and there's some really good arguments. It's something very interesting to think about, ponder that data and the evidence, and some of it also has to do with us trying to understand the mind of God. Like, when he created the world to look old, what does it mean when he says days in Genesis? Huge theological debate we're not going to get into here. But talking off of what this guy does, I feel like is a little disingenuous. Yes, you have the crackers, but please stop.
Oh, do I get the crackers?
Yeah, but don't make a huge noise eating crackers. Okay, so for example, here he says in this, I think it's just page 336, he says, where is it? He says, over the last 500,000 years, the average temperature of the Earth has fluctuated between 19 degrees Celsius and 27 degrees Celsius, and is it presently at the high point 27 degrees Celsius. So the idea is like, oh no, what are we going to do if we get too much, our glass gets thicker, we get too much carbon dioxide, and it gets too hot, and it'll be hotter than it's ever been in 500,000 years. Now, especially him coming from an old Earth perspective, this feels a little disingenuous to me, because the Earth is actually, like, life on Earth, going with like the data that they're looking at, life on Earth is much older. Like 500,000 years is just a blip. And so, like, the Earth has been a lot hotter than 27 degrees Celsius before. A lot hotter. And we also had much higher rates of carbon dioxide on the atmosphere with the fossil record and things that we did that with. And we got giant spiders and huge bugs and crazy tropical plants that loved it. What would that like be for us? That's another question. But like the Earth being, oh no, it's the hottest it's ever been in 500,000 years. It's a little bit like when someone says, this sports team has never, this is the most groundbreaking, victory ever. That no one scored this high in the last 3 years. Like if you look at, the fine print, it's like, oh, because 4 years ago it was way higher than that. You know what I mean? It's like one of those, how you present the data, where you decide to click, to start from in the story kind of changes like the whole argument there a bit. So then he gets down to the bottom and he talks about how you can never change only one thing. Change one thing and it changes another. This is incredibly true, especially in the Earth, especially in systems, especially with life. And he says about how a rise in global temperature might actually start the next ice age. He says, or it might not. We don't know. It could make it hotter. It can make it colder. We don't know. We don't know. So I appreciate him saying that. Because one of the problems with this whole, it could do that, but we don't know. Like, if you've ever looked up on the internet about these things could cause cancer. Oh, maybe they couldn't. We don't know. I remember someone was like, oh, if you eat these things, it might really hurt your grandkids. or it might not. And then another website's like, no, don't eat the other thing. The other thing's really going to hurt your grandkids. Like, at least with that, you can experiment, eat one thing, wait, and see how the grandkids turn out. That's what cultures have been doing for thousands of years by what they called poisonous foods and non-poisonous foods, right? They would eat it and be like, oh gosh, so-and-so's babies died. Don't eat that thing over there. That's poisonous. Like, people have been doing this for ages. That's one of the reasons I have a lot of respect for, like, traditional foods, is because it's not, just because, grandma knows best. It's because you're literally looking at thousands of years of that culture basically doing experiments on themselves and saying, don't eat that thing. Bad things happen. Like, it can, make it harder for your grandchildren to have kids. Or, people have been watching these things. So that's why, I'm not saying home remedies are always right. They were wrong about bite the snake and whatnot. But a lot of times mixed up in these cultural things, there is actually a scientific nut that they are sort of observing. Yes?
Because they thought tomatoes were poisonous because they put them on lead dishes, and then the acid leached out the lead into the tomatoes, and they ate them and died, and then they thought tomatoes were poisonous.
Right, but see, with that, they were using sort of scientific criteria. They're like, when we ate the tomatoes, it killed us. They were correct. It was just they were eating on the lead dishes. Well, anyways, so back to this. The one thing that I find with all these global warming models, and there's so many arguments to be said on both sides, and you can look it up, and so much to be said. But one of the things that I find frustrating about these global warming models is that they're so much based on conjecture. Like, if you actually boil down to these, like, scientific models, it sounds really amazing, and they've got like some trend that they've got here, and then they've got projection, and like the projection. Like, does this little wiggle here mean that it's going to shoot up to here, or does it mean it's going to wiggle back down to here? Like he said, there are so many factors in things like global temperature. It might start the next ice age, or it might actually make us hotter. We don't know. We are projecting so much from these little wiggles in data, so much about the future. Now, it's kind of like when you read this website and they're like, this thing, eat this thing, and it might totally give your grandchildren cancer. Like, I was saying you can actually test that, but it's like, at some point, you're like, you can't just be like, all right, I'm never going to eat tomatoes or, whatever, potatoes or whatever it was this website was telling me, or it might hurt my grandchildren. I mean, I could make that call. But a lot of these things are, on the global scale, these are unfalsifiable theories. Because we're not saying if we predict global warming, if global warming is true, we will see this in the next year, or we'll see the opposite. It'll get colder or get hotter if global warming is true. If you do that, it's really hard to work with a theory that's unfalsifiable. It's really, really, really difficult. And so that's kind of what plagues like all these like prediction models, is that a lot of them, they're dealing with models that we predict this one thing, but it could also mean the opposite. It's not that there isn't something real happening, it's that it's extremely like at some point you've got to make a call, you've got to decide, what do we do here? That said, the Earth is resilient. The Earth has been much harder before, it's had a lot more carbon dioxide before. The Earth is resilient. The question is, are we that resilient? That's the more important. The Earth, like, at the end of the day, it really comes down to like a religious belief. And I've talked to people, I've read many articles written by people who seem to have this belief that like human beings in our corrupt state are going to destroy the Earth. This beautiful, and the Earth is beautiful, we're going to destroy the Earth. This is just not, like when you look at the fossil record, when you look at things, it's just not, like, we're not all that. I mean, even if we had a massive, horrible nuclear war and bombed each other into oblivion, like, life would come back. Like the algae, that they, like...
We need a Death Star in order to destroy the...
Okay, stop. What I'm saying is life on the Earth itself, nature is resilient. Nature is really massively resilient. The question more is about, are humans resilient enough? We're much more likely to destroy ourselves than destroy the Earth. But with all these like models, you're way looking at like the future, what could it possibly be? And it kind of also comes down to your beliefs about the future. I mean, we all know people out there who are so worried about so many things that might cause them cancer that they eat like 3 types of foods and, are super, super careful. I mean, but like the question is like, what's your risk to benefit ratio? And some people say, well, because we might predict that the world will be destroyed and everyone will die, we must do everything we can to stop it, even if the model is really sketchy. Well, I can make an equally sketchy model for something else and say, hey, everyone, you need to do it my way because otherwise horrible, horrible things could happen. I mean, there's a great Dilbert cartoon about this guy trying to get funding for his proposal, and he says, if you don't fund my proposal, like, these things are going to go wrong, and the Earth will stop spinning. And the other guy says, if you don't fund my proposal, you're going to get this massive amount of locusts, and you're going to plague locusts over the land. And the boss says, I won't fund either proposal. That way, when the Earth stops spinning, it'll fling off all the locusts. I mean, at some point, you need your theories to be anchored enough in reality that you can make a prediction and then check your model against that prediction. I'm sorry, that was kind of a long ramble. But again, then what was kind of dark and religious, very dark and somewhat religious, is at the end, the last paragraph he says here in page 336. What we do know is that energy consumption is related to population size. Because if you don't have enough energy, you starve to death, and there's not a whole lot of people, or you freeze to death, or you get the idea. We are serious, whoever we is, we are seriously questioning the idea of continued growth. Please see Appendix E, exponential growth and doubling time. Very important stuff. So, this is straight out of like one of those dystopian novels, where they kill someone for every person that's born and those sorts of things. We are questioning growth, whether we should continue to grow. So it really comes down to, what do you believe about humanity? What do you believe about reality? Thomas Malthus, and I think in the 1800s, or maybe even I think it was the 1700s, he calculated the amount of farmable land, how much calories we could get from farmable land on the earth, the rate that people were having children, and he was like, we're all going to starve to death, y'all. Like in the next, 100 years or something, everyone's going to die. There's going to be more people than food that we can produce. And he was wrong. Why was he wrong? Because human beings are the most intelligent beings ever on this earth. And unlike the deer, when you get population boom in deer and they all eat the bark off the trees and the trees die, or they eat all the plants, and you get this boom and then all the deer starve and then some of the deer come through. Deer can't plant, deer can't farm. And what did the human beings do? They discovered new ways to produce so much more calories from the same amount of land. So Malthus was wrong. Instead of starving to death, look at America. Obesity is our problem, not starvation. You know what I mean? And we are learning new and new ways to unlock more agricultural potential of land that we didn't even used to think was arable. Yes?
Such as Mars!
Okay, so getting to that. So what Malthus didn't foresee is the human brain. The capability to come up with solutions, to invent new things, to find new ways. And so, tying into what she's saying about Mars, if human beings really are going to go and colonize other planets, how can we predict for that? How can we predict for, it looks impossible, but 100 years ago, if you talked about we're going to land on Mars, what would they have thought? With the technology that you have. If you look at the technology you had at the time, and you start freaking out, there's going to be too many people, what are we going to do? They've been doing that for a while. Because human beings are great at inventing new technology, figuring out new ways. There are ways that we could potentially build those floating farms on the oceans. The trash islands that are stuck in the doldrums on the oceans, those trash islands, because basically the doldrums, I've remember in sea stories, doldrums are where the air currents sort of cancel out, so you get a really still area of the ocean. And so a lot of these trash that people threw into the ocean ended up there, and it got just bound together by seaweed. It was called Sargasso Sea, if I'm saying that right, Sargasso Sea, because of the massive amounts of seaweed that would end up hanging out there, because it's, the ocean, other currents are moving, but it's hanging out there. And you end up with these massive networks of marine biology life, where the disintegrating trash ended up sort of becoming a holding place for all this seaweed and marine life and things. And there's different kind of fishes that need, more shallow, a surface, unlike the depths. And so there's so many ways that we have yet to explore, that we could make food, that we could explore, there are people figuring out ways to reverse desertification. I don't know if I'm saying that right. How the Sahara used to be a green place and then it dried, became the desertification and the sands going out. They're finding ways they call the Great Green Wall. They're still really working on it. They're trying to find ways to basically stop it and eventually to reverse it. So there's just so many ways that human beings have not unlocked our full potential. So, I really believe in the genius of human beings to figure stuff out in ways that, the doomsayers are oh, it's all going to go downhill. This is the best technology we'll ever have. This is the best we're all going to die. It hasn't happened yet.
Have people said that before?
They've said it before, with Malthus. And the other thing that hasn't happened yet, there's so much more potential we can unlock. So many more, even technologies that we have figured out that we haven't even implemented yet. So human beings are amazing, and if you really do believe that human beings will colonize the galaxy, you can't do that when you refuse to grow, when you barely have enough workers. You can't do that. If you and it does really come down to religion. How do you see human beings on the earth? Like, I've heard an argument for people that feel like a wolf has the same value as a human, and so for them, when the humans are growing and hunting down the wolves, they're like, you don't have no right to do that. Humans should reduce. But that is their religious belief in the value of a wolf as the same as a human. My religion, that's not how I see it. I see human beings as the most valuable being that there is. And so when I see human beings, saying we need to kill ourselves off because, for the sake of the planet, for the sake of the wolves, for the sake of that, I find that deeply anti-human and deeply disturbing because we are the world's greatest resource. And then on top of that, in religion, I believe, the Creator said to human beings, go forth and multiply, fill the earth and subdue it. That word, eretz, in Hebrew, that word it can mean like the land, the matter. That doesn't just mean earth. That could mean many planets. Go forth and fill the earth. Subdue it. Learn. Figure out new technologies. Go out there. Explore. I do think that humanity was meant to go out and subdue other planets and make them green and make them beautiful. And I've probably read way too much science fiction, but I think at the heart of it, it's true. Anyway, that was my long ramble about that. Sorry. All right, can you cut?
Okay. Wait, pause it or?
Pause, just cut. Cut. We have to start lecture 23.
Okay.